All right, hello. This is a discussion about the light unit with an emphasis on the problems in positive physics. Okay, so with light, there's a few concepts. One is that electromagnetism has a spectrum, meaning what we refer to often as light is is visible light, the light that we can see, which is violet, blue, green, yellow, orange, and red. This is on our physics reference table. But there's and light is a form of electromagnetic waves. We've spoken about water waves and rope waves and things like that. Well, light is an electromagnetic wave, so it is a wave of uh, electromagnetism. And an electromagnetic wave has a couple of properties. One is that it will travel at the speed of light in a vacuum. So we see this number down here, 300 million meters per second. That is the speed of light in a vacuum. And in air, it is basically the same. So I could say, or air. All right. So that's an important parameter that you just need to know, the speed of light in air. And all of this electromagnetism, these are all just different frequencies of electromagnetism. So the light that we see, the violet, the blue, the green, all the light that we see, as well as light that we don't see, infrared light, ultraviolet light. X-rays are just a name for for a higher frequency electromagnetism, also that we cannot see. Microwaves that cook our food, that is a little bit of a lower frequency electromagnetic wave that we also cannot see. And radio waves are basically light that we cannot see. So all of this stuff travels at the speed of light, which is 300 million meters per second. So whether you're talking about visible light or invisible light, infrared, microwave, radio, ultraviolet, X-ray, gamma ray, they all travel at 300 million meters per second. For the formulas in this unit, we've got a couple of formulas. Velocity equals wavelength times frequency is an important formula. We're also going to be using this formula, N, which is an index of refraction. And each different materials will have different indices of refractions. So N equals C over V is an important formula. And this formula, N1 sine theta 1 equals N2 sine theta 2. And this formula here, the angle of incidence equals the angle of reflection. These are all important formulas for this unit. And index of refraction, as we said, each material will have its own unique index of refraction. One that you need to know is air has an index of refraction of 1. But all these different materials, water, for example, has an index of refraction of 1.33. So when light travels in water, it's going to slow down. Diamond, 2.42. When light enters diamond, it's going to slow down. Okay, so let's jump into some problems. The first section of problems is known as the wave equation section. So when you get into positive physics, you'll see one section that is the wave equation section. And let's just walk through a couple of problems. Here it says a beam of green light traveling through air. Well, if it's traveling through air, you know the velocity, 300 million meters per second. So you just plug that in. So here we have green light traveling in air. Okay, and then it says has a wavelength of 5.39 times 10 to the negative 7. So that goes in here. That's your wavelength. This gamma, I mean, delta. No, that's not delta. That is gamma. Oh no, that's lambda, I think. This is is wavelength. Okay. So now we just use our formula. Velocity equals wavelength times frequency. And so you would simply plug in 300 million for velocity equals wavelength times frequency, 5.39 times 10 to the negative 7, and then just solve for wavelength. So simply divide both sides by the 5.39. You'll calculate, sorry, that was substituting for wavelength. What we didn't substitute for was frequency. So now if we divide both sides by this, we'll get frequency, and we plug the frequency in here. Okay, but the formula is velocity is equal to wavelength times frequency. So we substitute in velocity, we substitute in the wavelength that we know, and then we simply calculate the frequency. All right, another problem in this section, just to do another one, just to demonstrate it one more time, is pretty similar. So here it says a light wave traveling through air. Well, if it's traveling through air, we now know the speed, 300 million meters per second, has a frequency of 6.34 times 10 to the 14th. So that goes into the frequency. So we simply plug that in. And then we apply our formula, velocity equals wavelength times frequency. And we're going to be solving for wavelength. So divide both sides by frequency. So you get velocity over frequency. And you plug in your two numbers, and you simply divide. And you'll get wavelength, and that wavelength will go here. Okay, wavelength, of course, has units of meters. Frequency has units of hertz. All right. In this case, you're going to get a number. You're going to plug it in here. And the number you're going to get is going to be in scientific notation. So it's going to be something like, well, I guess we can spend the time to do it. 300 million divided by 6.34, right? So, right, so 300, 1, 2, 3, 4, 5, 6, divided by 6.34. So, boom, parentheses, 6.34 times 10 to the 14 hertz. Now, I had to put parentheses because if I didn't, it would divide by 6.34 and then multiply by 10 to the 14th, and I don't want that. I want it to divide by this product. Oops. Equals. Okay, so I get 4.73 times 10 to the negative 7. So this is 4.73 times 10 to the minus 7. That's wavelength, meters. Okay, so now it's asking, what is this in nanometers? Well, you remember from, I think it's page 1 of your reference table, that it gives all the metric prefixes. Well, nano means 10 to the minus 9. So we don't want 10 to the minus 7, we want 10 to the minus 9. Well, how can I do that? Well, if I multiply by 10 to the 2 times 10 to the minus 2, I really haven't changed this number, right? I've multiplied by 100 and 1/100th. I'm going to get the same number. So if I basically multiply this by 100 and then divide by 100, I'm not changing the value. But knowing your laws of exponents, keep the base, add the exponent. 10 to the negative 7 times 10 to the negative 2 would be 10 to the negative 9 meters, and 4.73 times 10 to the 2, which is 100, would be 473. So I can just rewrite this 4.73 times 10 to the minus 7 as 473 times 10 to the minus 9. This is an equivalent number. Now I can substitute my nano for my 10 to the minus 9. So this would be 473 nanometers. And how many nanometers do I have? 473. So basically you just have to move the decimal 2 places and plug in your value for nanometers. And then what is the color of light? Well, I come over here and I say, where does 473 fall? It falls between 460 and 500. Therefore, this is blue light. All right. But the main idea was you're using this equation, velocity equals wavelength times frequency, and you're calculating one unknown. All right, second set of problems. These are light in an unknown medium, unknown material. So out here we have air. So this is air, and this is another medium, another material. Okay, so this is some material. Could be water, could be plastic, it could be diamond, it could be corn oil, it could be lucite, but it's some other material. And what's going to happen is light is going to slow down when it goes into another material. Okay, so we know how fast light travels when it's out here in air, but it's going to slow down when it goes into another material. So what we have in this chart is two rows. What's going on with the light when it's in the air, and what's going on with the light when it's in a different material. All right, so it says a beam of green light. Let's look at what we're given. Has a wavelength of. Okay, so it just gave us the wavelength. A wavelength of. So we can plug that in. That goes here. They just gave us the wavelength. In air, they just told us that this is air, and we know the velocity of light in air. So we plug this in, 300 million meters per second. Also with air, we know the index of refraction of air. So we plug in 1 over here. We know the index of refraction of air is 1. Okay, travels through an unknown material which has an index of refraction of 1.9. So they just said the unknown material has an index of refraction of 1.9. All right, so we just plugged in the information that was effectively given in the problem. So can we solve, we know everything for air except frequency. Can we solve for that? Of course, we use our formula. Velocity equals wavelength times frequency. We plug in our velocity, and we plug in our wavelength, and we're going to be left with frequency. So frequency is going to be velocity over wavelength. We're going to plug in 300 million and 5.19 times 10 to the minus 7, and you're going to get frequency, and that's going to go here. Okay, so this is velocity divided by wavelength, and you simply compute it. All right, so now we know that. Now, there's something you need to know, and that is, we said when light travels from air to another material, it slows down. And as you can kind of see in the picture, the length of the wave gets shorter. So the length, the distance in the air from one peak to another goes from being relatively long to relatively short. So as it slows down in another material, the wavelength is going to get, at least in this case, the wavelength is getting shorter. So the question is, does anything stay the same? And the answer is yes. The frequency stays the same. So that whatever the frequency is in the air, it's going to equal the frequency in the other material. So frequency stays the same. So once I've computed the frequency in the air, I just copy it down because the frequency is the same. Okay? All right, so now there's only two boxes left to solve for. One is the velocity in the unknown material, and the other is the wavelength in the unknown material. Well, we can figure out the velocity in the unknown material using this formula. So we're going to use n equals c over v for this. N equals c over v to figure out the velocity, okay? So we're trying to figure out velocity, so let's just multiply both sides by velocity, divide both sides by n. Okay, so what is c? C is the speed of light in a vacuum or air, which is 300 million. And n is the index of refraction of this particular material, which is 1.9. We plug that in, and we're going to get the velocity of light in this unknown material. So we plug that in. Okay, and then last but not least, we now only have one box that we haven't filled in, and that is the wavelength in the unknown material. And again, we just use velocity equals wavelength times frequency. So wavelength equals velocity over frequency. So you take this velocity here that you have solved for and divide it by this frequency here, and you get this wavelength. So wavelength equals velocity over frequency, and you are done with this problem. All right, let me just do one last one, and then hopefully that'll get you a large portion of the way through. Last chunk of problems in this section, reflection and refraction. Okay, so what happens here is you have light being shined down on a surface. In this case, this is a tank of water. Um, and up here, this is air. It doesn't say anything. It's air. Okay. And what's happening is the light beam coming from the air travels down, and some of it simply bounces off the surface. That is known as reflection. When something bounces off the surface, that is reflection. So this is a reflected ray right here. Okay. So when the light comes down, bounces off the surface, and stays in the air, that is reflection. Okay. And the formula for reflection, as we discussed at the very beginning, is angle of incidence equals angle of reflection. So it's very simple. If it comes in at 69 degrees, it goes out at 69 degrees. So boom, we plug that in. What is our angle of reflection? 69 degrees. It's the same as the angle it arrived at. What is the angle of refraction? So that's this angle down here. I'm going to call it angle 2. That's the angle of refraction. How do we calculate that? We use Snell's law. N1 sine theta 1 equals N2 sine theta 2. Okay, so this up here, we're going to call this material 1. And down here, we're going to call this material 2. So what is N1, the index of refraction of material 1? Well, material 1 is air, and we know that the index of refraction of air is 1. Theta 1, this is theta 1. This is angle 1. It's our angle of incidence, 69 degrees. N2, that is the index of refraction of the second material, and that is given. And theta 2 is what we're trying to solve for, or angle 2 is what we're trying to solve for. And then you simply have an equation and you simply do the math to solve it. So we would divide both sides by 1.33. Compute this number, and then you would take the arc sine of that number. And you get that answer, and then you plunk that in here, angle 2. Okay, but this is the formula to use. N1 sine theta 1 equals N2 sine theta 2. All right, hope that helps.